And we're back. We're going to talk about lipids. Um, lipids are going to be fats. We're going to talk about fats. We're going to talk about these energy storage molecules. We're going to talk about phospholipids that we're going to find in cell membranes. We're going to talk about steroids, which we'll find in hormones. So lipids are one class of large biological molecules that don't actually form polymers. So remember, I think in our first video I said that the carbs, the proteins, and the nucleic acids all form polymers, but the lipids do not. And here we are back talking about that. So the lipids don't actually form polymers. What the unifying feature that we have in all lipids is that they have very little to no affinity for water. They're considered hydrophobic. They are hydrophobic because they are predominantly hydrocarbon in nature, so they're made up predominantly of carbon and hydrogen, and they form nonpolar covalent bonds. So those nonpolar covalent bonds, you'll remember from, I don't know, probably chapter 2 or 3, nonpolar covalent bonds share electrons equally. Water was a very polar molecule that we discussed, and lipids are very nonpolar. The most biologically important ones are the ones that I mentioned earlier, the fats, the phospholipids, and the steroids. So just remember that lipids don't actually form polymers, and that they're very, very hydrophobic. We'll talk about fats first. Fats are constructed from two smaller molecules, glycerol and fatty acids. Glycerol ends in OL, so you'll notice that OL ending. Glycerol is a 3-carbon alcohol, so any of those that end in OL are typically alcohol. Glycerol, ethanol, those guys ending in ol are going to indicate that there's an alcohol with a hydroxyl group attached to each of the carbons. I believe we're going to take a look at that in the next slide. And then the other part of the fats are the fatty acids, and the fatty acids are made up of a carboxyl group attached to a long carbon skeleton. So this is what we're looking at. Here's a fatty acid, specifically palmitic acid. Right here is our glycerol backbone, and what ends up happening is we have this long fatty acid chain. See that? Really super long fatty acid chain. And what's going to happen is we're going to undergo this reaction. You know what this is. We're pulling out water. We're dehydrating these two molecules. So this is a dehydration synthesis reaction between a glycerol and a fatty acid. And what we're getting is we're getting a fat. So this linkage that occurs is called an ester linkage. So an ester has a carbon, an oxygen, and then a carbon that's got a double bond to another oxygen and goes on to two more carbons. This is an ester linkage, the same way we had a glycosidic linkage in the carbohydrates. You want to remember that when we're forming fat molecules, this one right here is triacylglycerol. When we're forming those, that type of bond is called an ester linkage. So what you're looking at again is that synthesis or structure of a fat, specifically triacylglycerol. Remember that fats separate from water because water molecules form hydrogen bonds with one another, and those hydrogen bonds exclude the fats. That's why your oil and vinegar separate out. In a fat, 3 fatty acids are joined to a glycerol. Remember, those are ester linkages, and they create a triacylglycerol, or more commonly called a triglyceride. You've probably heard triglyceride. What are some characteristics of fats? They're insoluble, and we've been talking about why they're insoluble. It's got to do with that nonpolar nature of those covalent bonds. Fatty acids will vary in length, so based on the number of carbons, and in the number and location of any double bonds that may exist. So that leads us to talking about saturated and unsaturated fatty acids, and we'll hear about those dietarily. But saturated fatty acids have a maximum number of hydrogen atoms possible. So there will be no double bonds between the carbons in saturated fatty acids. We're going to have all single bonds between the carbon, and every other bonding site is going to get taken up. Every other possible bonding site is going to get taken up by hydrogen. In unsaturated fatty acids, what we're going to see is one or more double bonds between carbon atoms. Here's some pretty easy ways for you to remember them. I like lists. Lists help me remember things. So on the left, we've got saturated fats. On the right, we have unsaturated fats. Just looking at them, when you're physically looking at a saturated fat, typically they're solid at room temperature, so they're not liquidy. Whereas the unsaturated fats will be liquid at room temperature. Most of the saturated fats are going to be animal based, and we're going to have straight chains. No double bonds means that we don't have any bending or any kinks in them. The unsaturated fats are going to be plant based, so that's another way you can tell. Typically, if you know what that fat is composed of, coconut oil, for example, comes from a plant, so it's going to be unsaturated, and we're going to see those double bonds. Here's just the visual to help you remember that, and then I do believe there's the next one for unsaturated. So I just wanted to give you the visual, try and help to bring that home, give you a couple of examples of saturated and unsaturated fatty acids. That's going to be something you're going to want to know for your exam and just for life in general. Trans fat. Trans fat is something that it's a fat that behaves like a saturated fat by raising the level of the LDL, the low density lipoproteins. We mentioned them previously as being the bad cholesterol. The LDLs will increase the risk of coronary heart disease. Trans fat also increases the level of HDL, so the high density lipoproteins, or the good cholesterol, which help remove cholesterol from the arteries. So the net increase of LDL HDA ratio in a trans fat is approximately double to that when we talk about a naturally occurring saturated fat. So diets that are rich in saturated fats may contribute to cardiovascular disease. When we hydrogenate unsaturated fats to saturated fats by adding hydrogen, then we get things like hydrogenated vegetable oils. And so we get those double bonds in the trans fat. And I mentioned that only not because it's super vital to what I want you to remember from this course overall, but I want you to have an idea of what trans fat means when you hear it on television or on the radio, or you pick up an article, or you're reading actually something that you're going to purchase in the store. I want you just to have an idea of what that term means. Functions of fat. It's energy storage. In fact, it's great energy storage. It has 2 times the amount of energy. So if I take 1 gram of fat and 1 gram of carbohydrate, that gram of fat is going to have twice the amount of energy stored within it. Humans and other mammals will store their fat in adipose cells. The other thing that adipose cells do is they cushion vital organs. They're an insulator for the body, so they have a protective measure other than just energy storage. Whiteboard question for y'all. It's saturated or unsaturated, and why? How do you know? What do you see that allows you to decide saturated versus unsaturated? I'm gonna take a break in our video here. We're gonna pick back up with phospholipids, our next group our next subgroup here. But this is a great place for us to break because phospholipids are kind of a big topic for us. We're gonna do a lot with them as we move through this semester, and I want to have them in their own separate video for you to reference back to.